mapping. So here we're mapping out an understanding of relevant causal structure, particularly what depends on what influences what, at a high level, without going into all the details of exactly how does it depend. What's the exact mathematical relationship? How about another stage of modeling? Yeah, variable selection, excellent. And we'll see how important that is and how we can divide it into three categories. So what was another one? Yeah, formulation. There we're actually getting down to brass tacks. And what's the formula for this and how does it depend on that? Okay? So these are good points. So broadly, I drew this out here and drew a number of stages, and beginning with problem conceptualization, where a key goal is to identify really what you're after. What's the problem you're trying to solve, or the goal of the modeling? What's the research question you're trying to understand? One of the challenges of the sorts of modeling we're going to be talking about, and it's all the more prominent with agent-based modeling, which is extremely flexible, is you want to be very careful about putting things in, because it's very easy to add one more thing, but it can get in the way of insight, and it can certainly lengthen the model process a great deal. And so you want to be very judicious about putting things into the model. That doesn't mean you'll forever hold off necessarily. It may just mean you add things in one at a time, learn from that, grow in your understanding, and then choose what you want to add. Not just sort of throw it in there with the assumption you're going to need it. There's issues here of model scope and boundary selection also. So the research problem, I mentioned that all models are simplification, all wrong in a sense that our map is wrong. You have to think very carefully about what we want to put in. Just like with a map, its clarity is impaired if we put too many things in. We had a street map of Saskatoon. We tried to draw every tree on that street map, obscuring the street. If the tree obscures the street, the view from above, we'd have a hard time reading the map, because streets would disappear under canopies of trees. And where does that street go? We can't see. The trees are in the way. We don't want a map like that. We want a map that shows us the street goes here to here. So sometimes putting details in can obscure understanding up front. So trying to get what are we really after can help you, can act as a logical knife, as John Sturman puts it, to cut away unnecessary complexity. And there's this Yagni principle. How many people have heard of Yagni before? Anyone? So, sorry? Well, yeah, it's great if you heard about it in the lecture before the class. So, agile software engineering. There's this principle called the Yagni principle. You ain't gonna need it. And the idea is, look, keep things simple, focus on the things you know are needed. In that case, show it to the client, get their feedback, learn from it, and then figure out what to put in next. Because you could put all types of things in there, and it might not be what the client wants. It might not be what you need to put all sorts of things in. You put one thing at a time, you see how it changes things, learn from that. Is this getting you closer? Are there refinements that are needed? Maybe new priorities come up. And then you could decide, okay, what do we do next? What do we do next? So I tried to emphasize this very incremental modification process, okay? Building up a model in a step-by-step fashion. What are the advantages of that? Let me ask you. So why build it up in a step-by-step fashion? There's actually a whole swack of different advantages. Could you give me some? Okay, that's a huge one, particularly with agent-based models. But actually, more broadly with most sorts of dynamic modeling to a degree. With agent-based models, particularly key, because there's so many moving parts. Add one thing at a time, if there's a bug, you know, it's much easier to find where that bug is if you've only changed one thing, right? You can zero in on that bug very quickly because you've only changed maybe a few lines of code or added one transition or done whatever. So if something goes wrong, obviously wrong, null pointer exception, I mean, like that, you know where it is. But part of the challenge of dynamic models is you don't always know that something went wrong. Why is that?
Could be a model, a problem between other models being designed.
Yeah, that's
Does the model actually show what you're trying to do?
that's true. So maybe you built the model right, but maybe you haven't built the right model. Maybe you haven't built the model you kind of should have built to describe the problem. You built something that's describing something different. You've implemented it correctly, but it's describing something different. So that can go on in a big way. What's another reason why, even though there's maybe a silly mistake you made, a defect, as it were, a bug, that may not be obvious initially? This is very important. Sorry? Okay, yeah, it may not be very visible, but let me ask this: if I ran the Schelling segregation model, and I run this, so I'm gonna sort of get this randomized, and you know I could draw this here, and you know did you people expect to see that? Is it exactly what you expected to see at that setting? No, you didn't know what was going to come out of it, right? It's not like you're adding 2 plus 3 and you can look at it and say, is it 5 or not? Nope, it's not 5. Okay, gotta go back and fix something. Here, these models, by their nature, give unexpected results sometimes. They give results which we can't anticipate. They surprise us sometimes. And there's an unsettling question. Is this result, you know, is this result actually an emergent property of the model, something unexpected because of underlying dynamic complexity, something that just a combination of very, very simple things that interacted in complex ways, or the whole is greater than the sum of the parts? Or is it something where there's a silly little bug? So you see some odd behavior. Is that because of a bug, or is that because of some emergent pattern? That's often not obvious. And so when we see something odd, being able to know that, well, if it's a bug, it's just because it's a very simple thing I just did, it's really helpful. You can just double check, look at the things you just did, go through the reasoning again. If there's a really interesting pattern that's come because of that, it speeds you a lot to only have to look at a couple things, right? Lets you quickly go through it. That's one good motivation. But another one is, man, if that thing that you see, that unexpected behavior is real. In other words, it's not based on a bug, it's not based on some silly thing. It's actually a substantive emergent pattern. Now you know what particular thing triggered that. Because you've only made one change. You added one transition, or you added a certain state, or you changed this parameter to be something lower. And now you've seen the result. It's really interesting. So either way, ladies and gentlemen, when you see something interesting, you win because it was such a small change. You win because of insight, you win because you can locate the bug sooner. Does that make sense? You can spot the problems. This is no small thing in both cases, okay? When you build an entire model up, and it takes you months of work, you go through that whole process, and then you run it, and there's some behavior out, it can take a long time to find that bug. A long, long, long time. It can also be devilishly hard to know what part, like, okay, these really interesting patterns are coming up, but where are they coming from? This part of the model, that part of the model, some combination of them, to this other thing. and you have to do a lot more work. If you're just adding one thing in at a time, you recognize where those patterns come from much sooner. And ladies and gentlemen, that's not merely a convenience. You save yourself time. That's great. But the fact that you know earlier that there is such a pattern emerging may shift your priorities. It may change totally what you end up putting into that model. Because now you see something really, really interesting, maybe with a very simple model. And maybe it makes you think, do I really need to add all these extra things? Maybe I could get a paper up just on that. Maybe I could share these results with my client. Maybe I could, learn from this in my decisions for the next few months. Right? It brings that learning sooner, which is often key. Okay, so incremental development, I would argue, is really key. And it's really valuable to sort of compare behavior now against the previous version. What changed? Okay, so-called docking it. And sometimes you actually want to disable the new feature, make sure they're the same. Disable that new feature you added, make sure they're the same so you didn't break anything, and then add them, and then turn it back on. Okay, so to keep track of extra development. So lots of good benefits, and it's great for your morale too. You see a little bit coming, a little bit coming, a little bit coming. Kind of feels like you're making some progress. For the client too, feels like making some progress. Increase stakeholder confidence. You can get their feedback on what you're seeing earlier, etc. So you can secure feedback earlier. Okay. Very, very good stuff. So although I draw this process out like this, the fact is that this is best done in a piecemeal sort of way. Particularly, I would note the first couple of these, where we're sort of iterating to a model formulation. Sometimes we do these later stages very incrementally too, but it's typically with longer time constants because calibration takes longer, model testing could take longer. But we also often formulate the model, maybe test it a little bit, but not yet fully calibrate it and iterate sort of on these stages of the process, okay? So this model scope and boundary selection often evolves over time as we learn from the model. Qualitative, let's talk a little bit about this this purpose. So one of the most valuable divisions, I have a slide where it kind of shows an example model where you divided these up. So this is one of the most valuable divisions you can make. And I would ask you to consider all making it in the course of this project, of your projects in this course. What things are simulated by the model, changing in the model? You're actually simulating how they change over time. What things are in your model, they're represented, but they're just represented in a fixed way. And what things are ignored or excluded by the model? They're explicitly, you've considered them. In theory, you could put in, you could not put in, you decided now to leave them out. There's no shame to this. There's a huge list typically. And over time, you re-examine, you say, but by having a list of these things, having an explicit list, these are the things I put aside, it helps you re-examine. Why am I still not seeing behavior that's kind of like the real world system? Maybe I want to put one of these things in here. Maybe I want to shift one of these things to here. So are people comfortable with this endogenous, exogenous distinction? So what do I mean by exogenous? Anyone give me an example? Suppose I say I want to have a model of the Saskatoon economy for job creation and so on. Okay, and simulate innovation ecosystem in Saskatoon. There's U of S, and there's the innovation place, and there's startup companies, and there's funding agencies, and there's programs like including things like the IRAP program associated with NRC, and there's larger corporations, and there's agents who may be folks like you, going through school, sitting in classes, and graduating, or doing internships in companies, graduating, going being hired, whatever. So those could be all represented in this model. Suppose I said to you, okay, the availability of funding is exogenous. The availability of sort of funding for research projects is exogenous. What do I mean by that in that model?
You don't have any control hours.
Yeah, it means so the model is not changing, it's a fixed assumption about this. Maybe I'll say the availability of funding to fund, we'll assume the amount of funding available to fund research related to, maybe it's clean energy or whatever, in the model, or simulate innovations related to clean energy, the research money goes up like that. Or maybe I say it goes up and then it goes down. Some fixed, but the point is I'm predefining, this is time here, and I'm predefining how it changes over time. It's just telling the model, assume this. That would be an exogenous thing. I'm telling you ahead of time, make this assumption about how funding will change. Is it represented in the model? Yeah, it's represented. The professors in the model might have a chance of getting research funding depending on the amount of funding available and that sort of stuff. So it's represented, it's just represented in a fixed way. How if I said it was endogenous? What would that mean?
What is the output of the model?
Yeah, it's actually, now this research funding available is being simulated by, it's being calculated by, it's being computed as part of the model. It's one of the aspects of dynamics that evolves over time, part of the behavior of the model. So now, that availability of funding might depend on, for example, the success of innovation. So if there's more innovation success, it leads to more funding, the government putting more funding into this area. It captures that feedback there, right? That this research success means the government gets excited about it, or this commercialization means the government gets excited, says, oh, this is really practical, or we'll put more funding into it. And in that case, research funding would also be represented, but it might be represented in a way that would be highly dependent on policies that you could undertake. So maybe if you could make more efficient the process of finding students internships or training research from the lab to the field, then the amount of funding available from the government would rise because the government realizes the amount of potential associated. So we could have research funding be exogenous or endogenous, right? Does that make sense to people? So remember, in this model, we're simulating certain things are being determined by the model, and the question is research funding just being told to the model, assume this, or is it being determined by the dynamics of the model, by the number of interns there are, by the availability of professors to work in this area, or what have you. Does that make sense? Okay, so endogenous, exogenous, or we can say it's simply excluded. We could just assume that we'll abstract away from research availability funding. We'll assume each professor can hire, on average 3 to 5 students, per year for their lab or something like that. And that's just going to be our assumption. They can take 1 new student per year. We're not going to deal at all with the fact whether funding is going up or going down or how it's affected. We'll just exclude it. But we list it here. We say explicitly we ignore this, and we'll come back to it. You go through this reflection process on what's in there. Make sense? Okay. Okay, so, and I should emphasize, this process you're going to go through, particularly in an incremental process, you may go through this at several stages. So initially, my suggestion is you try to put just a few things in here. 1 or 2 things, maybe 1 or 2 things in here. And you have most here. And you learn from it. Try a little thing, oh, that's interesting. And then, having benefited from that learning, then you go back and say, okay, let's shift one of these things here, or let's shift one of these things here. Or maybe this thing we made endogenous, we really tested it, and it really doesn't make much difference, and it really adds to the complexity, or really adds to it slows down the performance, so we shift it here. So you shift back and forth, and you evolve the model. Okay. Right. think I'll come back to this process, but the fact is, if we have things that are endogenous, it lets us simulate certain types of outcomes we wouldn't be able to if it was simply exogenous. For example, we might see the effect of our intervention on stimulating research, which would cause a positive feedback because, if the research was successful being commercialized in the first place, it causes the government to invest more research, which allows even more commercialization, which allows for even more sort of demonstration of results and more economic output, and the government invests even more. So there's a positive feedback that if we made it merely exogenous would be not captured. So we might, if we were trying to estimate, like, what's the cost effectiveness of making some change, we might underplay it because we wouldn't realize just how much it can change in the system. So that's something to bear in mind. And I have some examples of this which we may return to later in the class, but I think I'll leave it out for the moment. So, particularly in the agent-based modeling space, there's this notion of pattern-oriented modeling. The idea is we notice patterns in the world. In system dynamics, we talk a lot about reference modes. Okay? Reference modes being patterns of behavior over time, which require explanation or are problems, or otherwise merit merit consideration or investigation. So, for example, there may be a boom and bust sort of situation where the number of the output of the farms rose and then it started to decline, and we want to understand why that was. Or maybe you have some situation where we've had declining enrollments in our program, or maybe there's a situation where there's a cycle. So our research earnings for our program have been cyclic in some sort of way, and we want to understand that. These are examples of what are called reference modes, is the word for them in system dynamics. And in fact, Benson supports, at least the full version, sort of encoding these within the model for explanation. Okay, they're called reference modes, and they're patterns over time. These are very prominent in the system dynamics literature. For example, people have analyzed why are the business cycles. Are you folks aware that the amount of economic output in industrial world sort of goes in these cycles? There's established cycles which have occurred over the many year time frame. There's actually several layers of cycles associated with particularly capital intensive industries like machine tool industries, etc. There'll be boom years and then it goes into a down period, and then boom and then down, and then boom and then down. And actually there's spacing between them, and system dynamics models have been used very well to explain causes for that, or in supply chains you can get these sort of cyclic behaviors. In computer science enrollment, you're seeing cyclic behaviors. What happened with computer science enrollment? Can anyone give an explanation? So one of the reasons people use system dynamics models to explain reference modes. Can anyone give an explanation? Why was there a cycle we see? So yeah, so and also but perceived. One of the things you realize in modeling is the powers of perception. It's not just what is the case that leads to feedback, it's what's perceived to be the case. So there was back when I was a young man, and you folks, some of you might have been born, there was, sort of modest computer science enrollments, and then in the late 90s particularly, it picked up in a major way due to the dot-com bubble. You ever heard of the dot-com bubble? So there was a dot-com bubble which popped in the late 90s. It was associated with great expectations about the internet, thinking everything was going to be transformed by the internet really soon, and people had sort of a millennial vision, and and really it wasn't very well grounded, and so tons of money got pumped into companies which spent it left, right, and center in ways that weren't very productive, and it all collapsed in about 99, 2000, particularly associated with the telecom bubble. So telecommunications companies were betting on the number of customers, doubling every 2 years or whatever, and it didn't play out. So there was this sort of big growth in the number of people coming into CS fields during that period. And then after that, people said, oh man, this is a bubble. We better not go into CS, we'll go into other fields. And the number of people going into it went way down. So I think at MIT, there was like 750 people in the undergrads in computer science program in there, and then I think it went down to a third that number, 5 years later or something like that, 250 people in the program. And then, a few years later, people started to realize, this actually isn't too bad. You can still find jobs, maybe not in Silicon Valley really easily, but you can find jobs in a lot of places still, and it's pretty good career-wise. You get pretty good salary, and so on. And so enrollments eventually started sort of lifting again, and then declined some, and then are lifting, etc. So there's actually these cycles, and cycles associated with perception, cycles associated with payment. How much do you get? Because a large numbers of people graduate, they compete for payment, and therefore they might accept a lower salary, etc. So these cycles associated with these things. These are reference modes. And in system dynamics, we spend a lot of time sort of drawing out reference modes. In a given model, we might have several reference modes, 10, 5, 3, that are of main interest. Maybe some are problems, some are for explanation, etc. In agent-based modeling, we have other sorts of patterns that also come into play in a big way. Can anyone give me some patterns based on what we've seen? Have you seen patterns before that might require, you might want to seek an explanation from an agent-based model? What sort of pattern, other than sort of count over time, number of people in a given state? What sort of pattern might I see? Do you see a pattern here? Is there a pattern? Yeah, there's a pattern. It's kind of hard to describe it exactly. It's not exactly cyclic in this sort of way, but there's a spatial autocorrelation, if you characterize it. In physics, they probably have some order parameter that they sort of be able to specify. There's autocorrelation in the, in the color associated here. But in light language, we could say that's clumping, right? There's sort of clumping of these things. That's a pattern. It's fully legitimate as a pattern. We might not be able to write it down as a sign function or something like that, but that's very legitimate as a pattern. And a lot of models actually in agent-based modeling try to explain these sort of patterns, like the Schelling segregation model. Why do patterns of residential segregation appear? Yeah, that's a pattern. So this is a spatial pattern here. If I look at this model, another agent-based model, do I see a pattern? Yeah, you bet I do. What's one pattern I see? There's a circle. The waves are propagating. There's a wave of infection. What's another pattern I see? Yeah, there's concentric circles, right? It's not just purely one circle. That's kind of interesting. There's a circle. Well, why isn't it a square? Why isn't it a hexagon? Why isn't it a star? There's a circle, and then there's concentric circles. What's another pattern I might see that I might want to explain? Sorry? Yeah, okay, so there's kind of sort of texture up here. Is that what you mean? Sort of it's craggy, right? Sequence of colors. Yeah, why is it that you have sort of yellow, then suddenly thick sort of red and then gray. You know, why don't you just see all mixed? These would be the sort of things that someone might come to. Now, you may wonder, I mean, do people really try to understand those sort of patterns? And the answer actually is yeah. For example, I may have had some. So by the way, I've tried to. Oops, no, not this one. I've tried to post the slides based on demands from a couple of people, but these are sort of patterns from. These are real data. This is data from England, in Wales. This is data from Saskatchewan. Measles, mumps. Okay. Do you see a pattern there? Is it totally random each year? No, there's sorry? Yes, there's flu season. Is it a sine wave? Not quite a sine wave. Is it semi-periodic at least? Yeah, is it perfectly periodic? Not really. It's kind of got some stochastics, but there's some regularity there, right? There's a regularity, but there's some stochastics. That's a perfectly legitimate sort of pattern. I say we want to explain this. This is a great example of a reference mode, by the way, in from a system dynamics. Here's another one: bubonic plague in England, 1722, I think it is. So weak number of deaths in thousands. That's a pattern. Bell-shaped curve. It's a classic epidemic curve. This is data from TB in the province. So we have individuals who are bridging between communities. So we have these kind of clusters of communities, and then we have individuals. This is data from a subset of a database I work with. These are different communities, colored by what community they live in, and they're connected to each other and close together. They're much more close together if they're connected, according to who they've mentioned as a contact. So when they get sick with TB, they could say, oh, I was in contact with these 30 other people, so those people can be tested as well. And so what this is saying is that people name as contacts, people by and large live in the same community. You might think that, they travel all through the province, and mention people all around the province. No, you mention people who are nearby by and large. So you get these kind of clusters there. This is another type of pattern you see, particularly for agent-based modeling. You can see it in system dynamics too. Heterogeneity, the fact that there's different types of people out there, for example, or different types of examples. They differ with respect, in this case, to their contact patterns. So there's a number of partners people have over a 1-year period. In this case, sexual partners, and you could see it's very long tail distribution. In fact, if we draw it out in what's called a log-log scale, if we ask, for numbers of sexual partners that are going up by factors of 10 here, what fraction of the population have that many partners? It actually matches what's called a log-log scale. So it matches what's called a power law distribution. Okay? So it's like X. It's the probability of having K partners is proportional in this case to probability of having K partners is proportional to K to the minus gamma for some gamma. Hence you take the log of both sides and you get a straight line. You get these sort of network effects. So networks and patterns in networks are a big thing in agent-based modeling. You see clustering in network, for example. These are big types of patterns. Spatial patterns as well. So this is chlamydia in the city, and you could see the high rates of chlamydia, certain sexually transmitted disease, are clustered in certain areas. Actually, that looks like, I don't know if that's Saskatoon. That looks to me like maybe it's Regina. But this is in Manitoba. This is rabies. Rabies spreads in waves, actually. You could see sort of high incidence here, and then it sort of lessens as you go out from this point. It sort of radially spreads out. This is in Connecticut. and that's kind of northern Connecticut getting towards Rhode Island. So it spreads out in these sort of waves around areas, and people have asked, where do those waves come from? And in fact, if you look at records, yes,
There may be lots of patterns, for example,
Yeah.
in our daily life,
yeah,
aging, the way season change,
Sure.
even the population, even for example, crowding in the boat, all are patterns.
yes,
A lot of we have a lot of this kind of patterns.
yep,
A lot of them are not meaningful or important for us. How can we
Yeah.
recognize those
Great.
kind of patterns, right?
we care about. Yeah, so this is this whole issue of model of purpose comes in. And generally you're trying to identify patterns here that speak to your, that you're quite convinced speak to your model purpose, okay? So, in other words, what is it you're trying to get out of your model, and what plausibly is important for, let's put it this way, if the model didn't capture certain sorts of things, what would concern you? So, I put it poorly there. What things would it have to match for it to be considered a real contribution, to be considered plausible as a model? Okay, so let's suppose we built a model that tried to address some problem you were interested in. What criteria would you have and say, okay, it really needs to at least look, provide an explanation for this thing, or reproduce this pattern for it to be plausible. Now, you're absolutely right that sometimes there's a whole bunch of patterns that could in principle be relevant to the thing you care about. So, maybe I care about, I'm just going to pick an example. Maybe I care about reducing absenteeism from flu here on campus, right? Maybe a lot of our employees are going for flu, and professors have to cancel classes because of flu and so on. I don't know if that's the case, but let's imagine that that's a concern. We could start to talk about all sorts of patterns of possible relevance, and it could, at the most obvious level, we might want number of flu cases over different years to see, is it really getting worse? Did it used to be better? Because that might clue us into why, right? Why is it worse now? We might look at for flu, how are those cases distributed? Is it an outbreak occurring like on campus? Like there's a spread of infection on campus? Or is it people just picking it up from people off campus? So we might look at the number of cases on campus over time, people who report having flu or people who are absent. And is it highly correlated? In other words, are they like all occurring at once, or are they occurring in a spread out way? Those might be things to be closer to home. But you're absolutely right. I mean, there's some patterns you could start to say, well, maybe the reason people get flu is because they're catching it in the bus. And we could look at patterns of, riders on buses and how that's correlated with their chance of getting flu. Or we could ask, what are the mobility patterns by which people come into contact, so we could lessen that. Generally speaking, this is the whole Yagni principle. You want to start with few patterns, okay? Just a few that you think are most important, and start there. And maybe it's just one, maybe it's two, and try to have a model that speaks to those, okay? That will capture some of the most salient aspects of those, okay? And try not to get yourself too complicated about things you don't know are for sure drivers of it. Now, later your research question may change. You may go from what is driving this to what can we do about it. Going from, in other words, a consideration of what explains this to, okay, now what can we change with confidence that it will lower this, it will make it better. And there you might start to look at, well, okay, what can we affect? we can affect maybe more easily advisories to advise people to stay at home, or maybe we can provide more hand sanitizers in the hallways, and so we can look at patterns of use. How does hand sanitization use correlate with chance of getting sick or whatever? We could look at those things, but you could just drown in data sometimes. If you're lucky, you have lots of access to data, and you could drown in it before getting insight. And so I would say start with just a few you're convinced are most directly relevant, and then try to learn from what you see, from trying to model those on a little bit of a basis, and then grow your ambitions over time. Is that at all helpful? Yeah. So I think the whole incremental development there is absolutely key. Because if you try to build a giant model that accounts for all of them at once, you build it all over 6 months or a year, and then you run it, sometimes you find yourself shrugging your shoulders because you don't know what really is contributing to what pattern. If it's not matching the patterns, you don't know why. You don't know why you see certain types of strange behavior. But if you build it up incrementally, you often where those behaviors come in, so you know where to go change things if they're causing problems. Okay? So, but ultimately, I think the way we're going to learn this as a group is predominantly by doing, and hence the projects. And we're going to be reserving a lot of class time for projects, okay, where we can work together and try to help you scope things. Great question. Any other questions right now? So I want to highlight that one of the things this question, your name is? Fahad. So one of the things that Fahad had highlighted, or helped point out is patterns. Which patterns you are concerned about relate to what the purpose of the model is. That's a key thing. Purpose is circumscribed very tight. Use fewer patterns, broader, more patterns. Okay. Now there's a great paper on this that I'll try to give you the reference to. But it's by Volker Grimm, Grimm, and it's in Science, second to top, most cited journal, and it's on pattern-oriented modeling. Okay, he's from a methodological background. He talks about patterns and modeling, and I'll see if I can get your reference to it, but you might be able to find it. Yourself quite easily. Okay. Right. So I want to highlight again that thing. Patterns are pieces of information which, if the model didn't ask them, it'll catch suspicion in the model. They're not merely things. Oh, sure. Take another pattern, throw it in there, try to have the model explain that. We are not, and I want to repeat this in the strongest terms. We are not trying to simulate a process in all its detail. Some of the biggest modeling failures of modeling projects have been when people said, we are going to simulate the immune system. There's this immune system that runs in the environment, we're going to simulate it. There's no limit to how detailed you can make that and try to go further and further to reproduce the patterns with very limited benefit to insight for particular key sort of problems that you're trying to address. Instead, what you should be asking is, we're trying to understand how the immune system, how interventions to improve immune system strength in people would lower the rates of HIV. We're trying to understand how variability in immune system strength is affecting the spread of flu in the population. That's a more sort of concrete thing, but to say we're going to model the immune system or we're going to model the transportation system, it's a fool's errand. As they said in King Lear, that way lies madness, because there's all these details you could put in. It's never going to be perfect. It's like we want a perfect map of Saskatoon. The only perfect map of Saskatoon, folks, is Saskatoon. That's the only perfect, and it's not terribly useful map. You can't put it in your car. At least I can't in my car. It's the only perfect map though, but you shouldn't be after that. You should be after an abstract. You should be after something that gives you what you need and it's useful. It can be done in a finite time. It can be done in a way that's economical, and it can be a way that yields insight for your particular question. Okay. Sometimes these patterns are very, very general. I don't necessarily mean they have to be over time. They don't have to be really over space. They could be something like gonorrhea rates are higher among women than men. That could be a pattern we need to account for in that model. If we didn't account for it, it would be viewed as kind of suspect or not of value. It would lack, our stakeholders would lack confidence, our clients would lack confidence. Okay. Okay. Now, patterns play a very important role of this sort, play a very important role in testing a model too. Because often what we'll do is we'll try to get it to match up front certain patterns. Other patterns we will put aside and then see if it automatically reproduces those without us trying in any way to make it reproduce those. Okay. So for example, in this process called cross-validation, we'll put aside some data and we expect the model, we don't use that data in building the model, we don't use the data in refining the model. Instead, we test the model to see if it predicts that data. This data we didn't use to create it, okay? Right. Some of these patterns may be at the individual level. In an aggregate model, that's hard to capture, but in an agent-based model, that's easier to capture at an individual level, or these sort of patterns. Okay, so I could show lots of other things, but I want to highlight the role of some additional stages here before we finish. One thing here is the issue of qualitative mapping out what's going on within a model in a qualitative fashion before you make it quantitative. And this comes in different modes. So within system dynamics, we have causal loop diagrams, which we saw last time, but we also have so-called system structure diagrams. For some reason, I don't have a qualitative, I don't have a purely causal loop diagram shown here. There's some wonderful examples, but this is one that meshes together stocks and flows, but also these feedbacks involving other factors. So, for example, there's a link here from malnutrition to AIDS progression. Typically, this model will be a model that we create to help us think through an issue, and an actual simulation model might only capture a small subset of this. It might eventually include more, but it initially captures just a small subset. Here's another example of a flow chart. Is this fully quantitative? No. But it gives sort of an understanding of how the process works that we want to represent in our model. State chart isn't any logic state chart, but we could create this long before we have any sort of exact data for these things, before we have rules by which it will run, before we have any code associated with it. There's another state chart. There's another one from AnyLogic showing several parallel state charts running in parallel. UML diagram, person, main, the environment associated with thing, a database connection. It's from a student of mine's thesis. This is a depiction of sort of what's in our model before we actually perhaps build the entire model, what we plan to put in it. It can be useful for thinking through. Here's another state chart. This is from a more sophisticated etymologic model that we'll be seeing, built by a student from this class a couple years back. Okay, model formulation stage involves getting down to brass tacks with actually putting things in place that are quantitative. And in stock and flow models, this is stocks and flows, and the formulas driving the flows and initial values for the stocks, values for particular parameters. With an agent-based modeling, it's a large modeling vocabulary, and I have it here. Events, we'll see. Multiple mechanisms like state charts, stock and flow, for evolution, multiple types of transitions, multiple types of agents, networks in spatial environments. This is going to require more discussion. In stock and flow models, it's a smaller modeling vocabulary, but it's extremely powerful in system dynamics. You build up things out of them, very, very simple building blocks, extremely powerful results. With agent-based modeling, there's a much bigger toolbox that you're drawing on. Okay. I think I will leave this for now, but I want to leave you with this slide as a provocative slide. So one of the things we talked about when we talked about model boundary was endogenous, exogenous, and ignore. And those are useful, extremely useful divisions, very fundamental ones. Another thing we want to ask about in an agent-based model are these questions here. Who are our agents? And some of these get into more advanced things we're not going to have time to really look at in the course, but a key one for agent-based modeling, and in fact for system dynamics to a degree, is to what degree are results pre-programmed versus arising naturally out of a myriad of interactions. We can pre-program in certain things. We can pre-program in the amount of funding. To what degree is the amount of funding arising from a combination of things, including changes, policy, so we put it into place? To what degree do we pre-program in contact patterns? To what degree do those result from, say, mobility patterns, where people are located, driving contact? To what degree are we assuming something like waves of infection? To what degree is that just coming out of it? That's something that has to do very much with this endogenous, exogenous distinction. Here's another issue, though, adaptation. So how does the evolution of the system lead to entity behavior change? To what degree does the evolving character situation around people, say, lead to the changing their behavior? For example, when flu takes off each year, people are known to sometimes exhibit what's called changes in their risk behavior. In other words, they have risk perception. They perceive there's a danger to themselves. What's one of the responses they may undertake to a danger? If they know lots of people around them are sick, what might they do? They hear people sneezing, hear people coughing. Keep a distance. So that's something they might not try to sit closely or spend as much time with those people. Another thing what they might do is do what? If you're on a plane and you hear people coughing around you, what's that? Yeah, exactly. Yeah, masks sometimes. I was once on a Singapore Airlines flight. I think it was 17 hours long, maybe 17 and a half. I think it was from Singapore. It may have gone to JFK. It may have gone to Los Angeles. I can't remember which. But they actually went through the plane and handed out masks. This is during the H1N1 pandemic, this is during SARS pandemic. So they were handing out the masks just like they hand out towels, hand out masks, and you would wear this mask during the flight. Believe me, I wore the mask. It got kind of, after 17 hours, it was kind of, you take it off to eat and then you put it back on. But another thing they do is wash their hands. Washing hands is a big one, with good reason. It's quite effective. People adapt. How about sensing? So, to what information do entities need to sense things around? So, suppose you're simulating how traffic jams. Why do traffic jams form at certain places in Saskatoon? You could have just cars. You just say cars go from A to B. This many cars go from these 2 points, etc. And you could see if you could simulate the traffic behavior that way. That's fine, but that's not going to capture the effects of certain changes. For example, straightening the road out instead of having a bend in it, or having a sign to sort of slow down at a certain point, or being able to provide information on a, I don't know if they don't do it here so much, but in the States it's really big, in like LA, San Diego corridor, they'll have a overhead which says how many minutes to so-and-so, so you know something about what's gonna go on ahead and if it's probably backed up. So sensing, how do the drivers in the model kind of have a line of sight and they kind of see what's ahead of them and they slow down, they see a brake being applied ahead of them, so they apply their brake. That'd be an example of sensing, which might allow you to pick up more naturally what's going on, and in fact, in a way that's more sensitive to some of the types of changes I mentioned. Are agents trying to seek some goal? Are they trying to minimize the time going to B so they could choose their route? Or are they just doing it in kind of a robotic sort of way that's pre-programmed? To what degree do they learn? Do they say, wow, I spent 45 minutes going across the Circle Drive Bridge yesterday. 45 minutes getting across. I'm never going to go that way again. After that, I'm going to go by the Southern Bridge. Do they adapt their behavior based on their observation, but then learn from it and change their behavior from then on? This could be key if you really want to understand the effects of closing a traffic bridge permanently. People learn. They say, I'm never going to do that again. I'm going to always go this other way, or what have you. Prediction. Do they kind of anticipate, okay, if it's taking me this long to get here, I'm going to go a different way, for example. Do they interact? Does one person call the other, say, I'm stuck in traffic, don't come this way, go another way? Do they interact in some other fashion? Kurt's group, during a recent workshop we had, a boot camp, they were looking at how people interact with cell phones in traffic in LA. So like when they're in a traffic jam, someone may not like to text on their cell phone while driving, but they're in this traffic jam and it's going really slow and they see people around them and they're all texting. And they say, I want to text. And they grab it. And then they get into an accident sometimes, which may make them learn, and then they don't do it again so readily. So interaction can occur, and particularly physical proximity, seeing someone who's doing something, seeing someone vandalize something might make you more, change your behavior in some sort of way, maybe more likely to kind of be intimidated or what have you. Are there stochastics? Is the model deterministic or stochastic? By and large, the system dynamics models we'll be looking at are deterministic. The agent-based models are stochastic, but you can in fact have invents and stochastic system dynamics models, and you can have, in principle, deterministic agent-based models. Those are pretty rare, but you can have them. And finally, to what is the model reporting? So it's running over time. Great. It's simulating over time. What are we reporting back? What is its output? What is the model giving us as a result? If we want to learn from the model, it has to tell us something. And we probably don't want to know everything about the current state. Maybe we want some summaries. Maybe it's an agent-based model, but we want to know those summaries that are perhaps summarized at the very top of the screen, like this. We want to know perhaps these counts which are up here at the top of the screen. Or maybe we want to know something about, the cumulative number of people who have been infected thus far. Okay? So this will be, we want to be thinking about what output is needed, and this is an example. By and large, we'll be outputting to files, we'll be outputting to databases, we'll be outputting to sort of user interfaces, and we want to think about what processes operate to gather that information. Those processes might not affect what's going on here, but they help us learn from it, help us understand it. And similarly, in a system dynamic model, we are often interested in certain, maybe we'll create a, I'll show you how you do that. You could create a little thing here, which maybe is going to output information on the fractional prevalence over time, and it'll just be a graph. And so maybe that's a key measure that we want to be able to feature to users when we demo our model, or we show them the results of different policies. We want to be able to have that so that we can, run a baseline alternative, and then we can modify by assumptions here. Okay? So there we go. So this is an example of an output here. So that's an output from the model. Okay, so that's all we're going to have time for today. We're going to start, following this lecture, we're going to start getting into issues of the first of the major types of modeling. We'll be looking at system dynamics. We're going to take a look at causal loop diagrams. We're going to take a look at learning about feedbacks within a system. How do we decompose our understanding of the system into feedback? So I'm going to ask you once again to review a video, and then we'll try going through some exercises, perhaps doing some building of causal loop diagrams. I may ask you to do a little exercise at home, which will ask you to build a causal loop diagram, and we could look at them, try to refine them here in class, okay? Because it turns out it's an art to really build them well, and you can improve greatly over your initial sort of impulses, often with a bit of guidance. So thanks very much.